Hello, everyone, and thank you for attending today's webinar, Generative AI at the Edge. This webinar is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Pat Lawler. I'm a Director of Technical Marketing at Qualcomm, and I'll be the moderator today. Before we get started, I'd like to go over a few housekeeping items. At the bottom of your screen are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout the event. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A widget, and then click the Submit button. We'll answer questions after the presentation. Also, if you're experiencing any technical problems, please type your issue into the Q&A widget, and we will be glad to offer assistance. I'd like to now introduce our presenter for today, Joseph Soriaga. He's the Senior Director of Technology at Qualcomm AI Research. Joseph, please take it away.
All right. Thank you very much, Pat. Thank you, everyone, for attending. This is going to be fun. Very excited to be able to share this with you today. I think we all know generative AI is taking off broadly. Examples like ChatGPT and Stable Diffusion. Today, we're going to be going deeper into Qualcomm's role in bringing this to the edge. Sorry for that. Let me make sure we're okay. All right, so today we have quite a bit that we're going to cover. Right now, it's structured as follows. We'll have some background on generative AI and why it's on device is key. And then we'll have two deep dives, one into Stable Diffusion, and this is largely covering also what we would say is large vision models, LVMs. And then we'll talk about full stack AI optimizations on the LLM side. And then we'll look at a case study with Llama 2, the model that was released from Meta this year. And then we'll close it out, tying this together also with hybrid AI technologies. As we bring things to the edge, it also opens opportunities to tie things in with the cloud better than they are today. And then we'll finish off with a Q&A, and yeah, we'll wrap up from there. I also want to say at the beginning that this talk today is from a AI research standpoint, not necessarily a product standpoint. So AI research, we like to think in targeted terms of, we start with fundamental research. We think about what are these AI ML technologies that are being researched actively? What are the surprising things that are coming out? And then think about applications, how they might be integrated in various things that Qualcomm's very active in, like multimedia on your phone, or compute, or wireless, or autonomous driving, in-car entertainment, all sorts of applications. We look and see, well, how well do they integrate with that? How much do they improve where that is right now? And then together with the fundamental research as to what is the ML model, what is the task, how is it integrated in a system, we look at the platform. And the platform has many questions around it as well, from distilling the models down to running it on the hardware, thinking about compilation and so forth. And we look at this from a research standpoint, and putting it together helps us as a company to anticipate the emerging needs in the commercial ecosystem. And then we work very closely with our partners on the commercial side. Now, the other important perspective that we take at AI research is to think about things from a full stack perspective. So much like the previous picture, I now put this more into a life cycle where we think of, let's say the fundamental area is related to vision. We try to identify a core problem in the vision application and see how to integrate it there. And if it looks good, through, let's say, like a simulation case study. That invention, we'll see if we can take it through all the way to the stack. So we'll look to optimize the model now to run more effectively on device, along with compiling it into the runtime, trying to leverage a lot of the tools that are available through our Qualcomm AI stack and taking the best out of what our accelerators and our AI engine can offer. And then we come to a proof of concept. We'd like to see an overall end-to-end application to make sure that it does run as we would like, even in an everyday situation, as much as we can represent it. Because running things on device, of course, are contending with a lot of other resources, and it's important for us to understand what that's going to be like. And then eventually, this helps us to seed ecosystem collaborations as we go through, and then eventually it reaches a broader adoption. We've been doing this for many years, and now we're going through this cycle at a much bigger scale now because Gen AI is at a much larger scale in terms of model sizes. So we've been really excited on this throughout even the end of last year, and our excitement, I would say, like exploded when we got to MWC because we were able to finally demonstrate one very large model running on device in a very compelling user scenario where we could render a text to image at the time, which was the running on Android phone. Some may have said it's the first, some may have said it's even the fastest, but in any event, it was fast enough to be interactive and to show it at MWC. We were very excited that getting this to be rendered in less than 15 seconds, people could try all sorts of things to see generative content, and because it's such an open set of text prompts people could put in, it was people loved it so much that it was acknowledged as MWC award-winning. Now, a lot has happened since then, and it's incredible that we got so excited, and now we're sub 1 second, which I'll talk about later. It's probably good to just remember like generative AI, what it means. Very at the basic sense, it is AI models that have been built to just generate content. Sounds very high level, but what's been really interesting is that, okay, if it generates text and then you give it a prompt, some of the text it generates actually is a very reasonable answer, maybe very relevant to the topic. And then as people have been exploring this more, they see that, well, maybe some of the answers sound like it's reasoning. So then it becomes a research question. Are these LLMs capable of reasoning? Because it's not necessarily encyclopedic knowledge that it's retrieving for you. And that's kind of the space of ChatGPT, and even code generation on the right is very much similar vein. People may ask a coding question, and then is it retrieving code, or is it actually producing code exactly the way you want it? It may not even be in whatever repository was used to train it. On the image side in the middle, a similar area where originally it's just generating images. It's very interesting to see the images that are coming up, and people start asking prompts that have combinations of concepts that may not have ever been seen. And then we start to see, oh, this is kind of interesting. This is content creation beyond maybe what's interpolating between what's happening. And then you go further and we start to see that if we apply it in editing use cases, now it's actually editing an image the way that we might want to edit it. And so we see that this idea of generating content becomes very, very useful for advancing applications. We can start to think broadly about the AI ecosystem for this. There's like very quickly, there's like existent applications that are built on foundational models that are trained kind of general purpose in a sense. And then they're also may use their own models specifically for application. Foundational models themselves may be domain specific or even general in the sense of the domains. So a lot of things can happen here. And of course, there's an infrastructure behind it and the tooling for managing the models and building them, training them too. So there's a lot going on that is It's very fascinating how these are accomplished. And then as I spoke before about what the models are capable of doing, it's very natural to think about where the applications be. So XR, where we want to just generate meta worlds, this is very natural to think about generative content that way. But on the other hand, in the very real world of automotive and say autonomous driving or assistance, driver assistance, some of these decision plans or prediction could be leveraged using generative AI. Now, assistants are becoming more commonplace on the PC and the phone, and you can imagine that you already interact with these already. But the level at which conversational AI is going to advance with LLMs can change this dramatically. And with all the things that are on the phone and on a PC, the ability to manage that more fluidly and more naturally through human interaction can be a game changer from a lot of people's standpoints. And of course, a lot of these things can translate to IoT very naturally. Now, these are intuitive use cases, I would say. An interesting use case that people we know about in research, but then may not be broadly understood, is that diffusion underlies some important other aspects. We had another research webinar earlier from my colleague Taco Cohen talking about robotic motion planning. And some people solve this problem by also looking at taking diffusion models and understanding how to denoise a set of trajectories and get a good trajectory out of a particular planning problem. It's kind of a lot to process right now because I haven't really talked to you about what diffusion and denoising is, but I'll get to that. And I just wanted to point out that it's not just generating pictures. There's problem solving and optimization problems that people can tackle with this as an engine. Now, these are two particular cases, LLMs and LVMs. The other reason for our excitement is that so when we think about what are our end devices capable, our phones or our computers or IoT devices that are front facing for us when we go around, those may have certain capabilities in terms of the model sizes that they can handle, somewhere up to 1 billion or 1 billion to 10 billion, I should say. And then when we look at what people have been accomplishing, at least in research frameworks and then early like pre-commercial prototypes, a lot of tasks have been demonstrated with some very compelling capability and accuracy. So right now we're seeing broad adoption of, say, text-to-image, dialogue, programming, but also reasoning, combinatorial optimization, image understanding. We're starting to see actually a lot of image understanding now come up. But it can continue to go on, even to collaborative robotics. And this is where we're just at the beginning of everything. Interacting with the environment, not just producing content, not just responding to what you ask, is like the next kind of inflection point, we feel. And it's great that a lot of the models that are being used to demonstrate these capabilities are within the range of what we can bring on the edge. Now, an important theme, I would say, through the day, although this is not the only thing that is taken advantage of, is knowledge distillation. It's very common to think of bringing these big models down to the edge through knowledge distillation, just on making them smaller, meaning the cloud model could be a teacher, and then we construct a smaller model of a student, and then use the teacher to provide not just answers, but actually logic. So labels of like a distribution on why among the possible answers, how that should be taken into account. And then those would be used to train the student model. This is an old practice in terms of like the AI research evolution, but it is very important and also you'll see a lot of it leveraged today. It is nominally a way that we can get a student to be as good as a teacher if the domain has been suitably reduced. Otherwise, you'll see that we also have ways of not necessarily making the model smaller, but improving the efficiency of the model in different ways, and still using this notion. And then it's good to just reflect on why we think that it's important to bring things to the edge. Of course, being a wireless company, we've been also purely focused on leading and making sure connectivity is the best that it can be with 5G and then going on to 6G. But bringing AI to the edge is also urgently important for us to look at, because we can now bring privacy, keeping everything on device. Reliability is there. If we don't need to necessarily maintain a high throughput for certain applications. And in particular, when we're now trying to move things towards more conversational, like if the camera is always on, microphone is always on, it is nice that we can leverage a lot of edge AI instead of having to ship these raw samples back and forth and maintain a low delay. Of course, there is a cost benefit too, in terms of how much we can offload from the cloud, as well as energy benefit. And then overall, because we can work on device, and because there's some privacy of keeping data on the device, there's a benefit that we can further personalize based on what it is that is local. So these have been always themes of any AI application, and even they still have very, very big relevance for generative AI. So this is where we continue our focus. So let me go into the first section, where we talk about Stable Diffusion and essentially LVMs. So for image generation, there's a notion of, let's say, diffusion and denoising, or diffusion is more the process of adding noise. And in this series of images on the left, you can see that we have a noisy image that can be produced. So we have a nice clean image at the bottom, and then diffusion would actually add noise to it, and then you would have this kind of Gaussian representation almost. But then in the other direction is denoising, and then we have a reverse diffusion process that we can represent a very nice image from this. And so on the right is how do people how do they design text-to-image networks leveraging this diffusion process? And so you might have an input prompt like this vase in Greek style with an intricate patterns and design, and then you run it through and you get an encoding, text encoding to represent that in a latent space. And then that ends up going to the denoising network, which is our UNet in this picture. And that goes through several steps in the UNet. And then eventually that is being denoised in some latent space. And then we go and decode that into a nice high quality image. It's very interesting that this was devised to work. It's actually quite fascinating, the things that are behind it. When we look at the bottlenecks of this, we see that, okay, there is a UNet that's almost 900 million parameters that it's running. And it's running, to get good quality, we're denoising this maybe 20 times or more. So very quickly we see that's where the bottleneck is, and getting that from 15 seconds down will be the core challenge that we look at. So if we zoom into the UNet a little bit deeper, you see, okay, the UNet has several layers, and here's why it's called a UNet. You have this kind of U shape where layers are going across and also through different sizes. And then we find that we can look at pruning some of the attention in the first layer. And then that pruning of the attention has a big benefit to reducing the compute as we go through the UNet. The Gmax can be reduced quite a bit. And then on top of that, we can, if we may have some loss in accuracy, we can take the teacher originally that didn't have that pruned and use it to distill this new network where we just removed attention in the first layer. And by doing this, we can have some improvement, maybe not a dramatic reduction in the number of parameters, but a dramatic reduction in the compute. And that's what's important for reducing the latency. Now, another example of distillation to speed this up is, here's another pictorial representation of the UNet. So now each block is the UNet again. And instead of working within the block, what we're doing is we know that we have to run the UNet multiple times to iterate. And so we will take essentially 2 iterations in this example as a teacher. And then we'll train another UNet as a student that tries to do what the teacher did in 2 iterations in 1 iteration or less. And so this approach to distillation helps us to reduce the number of iterations and speed up the rendering of the image. As you can see, this is we're not necessarily changing the model, but we are getting the model to be more efficient from a different perspective. And in this part of example, 2 to 1 is a dramatic reduction. So if we went back to February, 15 seconds would go down 8 seconds just by doing this level of distillation. So these are 2 examples of how we can take that network originally and then make it run more effectively on device. We can put together a number of steps, and that is how we're able to take ourselves from where we were before to our current, let's say, fast stable diffusion, where we've gone and changed the network and distilled it and optimized it. So efficient UNet, there's something that also we can do, which is guidance conditioning. It's another, leveraging another aspect of the network and using distillation again. And then of distillation, which I talked about. Now, if we look at the baseline model, and it's normalized to be running on the same device. So in the latest Snapdragon Gen 3, if we were to look at running that Stable Diffusion 1.5 version, we're at about 5 seconds of rendering time. And then if we look at now the distilled model following these steps, we're getting almost a 9 times better reduction in the latency to get to the final image. And then I'll show you some pictures after this about how well it rendered. But generally, you can think that we can also look at statistics of quality like FID and clip, and then compare that to the original and see how well that lines up. And they're also fairly good, very good for demo quality. And you can imagine if we put more data in the training, we could increase these even further. But for the most part, we have a very compelling illustration of running image generation at sub 1 second. And to give you a sense of some of these images, we can look at some of these prompts that we shared in the past, or people could have typed similar things. And the bottom is showing what the original model was doing, and then the top is showing what this new model is able to generate. And they're not going to be 1-to-1 in terms of like pixel to pixel, but you can see that the content is perceptually very much high quality in terms of it's matching the prompt. It is rendering much of the detail that you would have wanted to see, and also that it is, like otherwise very compelling in terms of the composition of what's in it and how much it's reflecting the prompt. And then as you kind of glance at these, I can show you too just what it feels like to see a 1 second rendering or less than 1 second rendering. We had this demonstrated at Snapdragon Summit a couple of weeks ago, and it was quite amazing. It's funny. It's faster than the slide transition. As I flip through the slides, you can already it takes longer to see that than to actually see the image get rendered. But we went through here just now, as I'm talking, we went through several examples, and you can see how quickly it renders. And it really opens up the imagination for how much you can now tie this in with applications. And also how much promise there might be for video one day. Now, to recap, this is kind of the the case study that we did on Stable Diffusion, you could say, and looking at it in just taking a step back and highlighting the things that we went through. We started off understanding that at the system level, it's a diffusion process with iterations and there's a bottleneck. And so from a system standpoint, we took this optimization to, let's see how much of the whole process can we distill from the steps to the model itself. And then we go through and we leverage that in making the model smaller and also otherwise training it to improve the iterations and so forth. Now, that's a part of the system design that's key from our research standpoint. And then it's important to then leverage the tools that we have. So the AI stack from Qualcomm, the AI engine, also the accelerators that we have, like the Hexagon NPU that we have, and the Gen 3 version. These are, significantly accelerating the machine learning models that we've already distilled them quite a bit, but it really takes this other aspect of the hardware and the software that's provided from Qualcomm to be able to realize that on device. And putting all these things together is when we can look back and see, oh, here's a nice application which I just showed you, where we can realize all of this. And this again comes back to our idea of wanting to go through the full stack and seeing everything come together and ensuring that by design we can achieve what we want. This kind of thinking is broadly applicable to LVMs that are as they're related to diffusion. So it is something that we really look forward to in onboarding more and more models on the Snapdragon platform. Now let me switch gears to the other topic of looking at large language models. So in this case, we want to think about what is the bottleneck in running large language models. And it's really about this autoaggressive nature of the language model. Autoaggressive meaning it generates each token, and it can't generate the next token until it looks at what the last token was that was generated. And that keeps going sequentially in that fashion. Now, as it goes sequentially, each token needs to go through the entire network to generate the next token. And as these networks are large, like 7 billion parameters, for instance, on the smallest Llama 2 model, we have to run all of these weights into the compute unit to figure out what the next token will be. So there's a huge bandwidth impact to running these models. We would say these are highly bandwidth limited and not very compute limited, because the amount of compute they're doing per weight among the billion parameter weights is much smaller than the bandwidth we need to move. And you can imagine, like, as we want to generate tokens as at the speed that you can read them or speak them, that's a lot of bandwidth movement that we're doing. So the very first thing that comes to mind is let's shrink the model in terms of quantizing it. So a lot of models are trained and they come out as floating point FP16 models, and we want to reduce them. And we've been very actively looking at int4 weight quantization, 4x8 activation, 8-bit activation with 4-bit weight quantization over the past few years. And it's perfectly timed for this application, because now if we went from FP16 to int4, we have a 4x reduction in the size of the model. That also impacts the latency, because we can move the weights back and forth from the DRAM to the compute, and also the power consumption gets better. Now, the challenges for quantization are that we do want to maintain the accuracy, and sometimes just directly quantizing the model without any data or any training data sometimes it can work, sometimes it can be reducing the accuracy more than we'd like. So then we would want to take it and do quantization-aware training. And then the other challenge arises is what kind of training data do we have that's available for this? And so this is where one of the innovations on the research side was, can we do quantization-aware training leveraging knowledge distillation? And the reason why is we think about this is the data, or I should say the training pipeline for LLMs is quite sophisticated. As you may see in literature, there's supervised fine-tuning based on instructions. There's also reinforcement learning on human feedback. A lot of different ways to align responses from the model to how conversational or how certain tasks are structured from a human perspective. And it's important to be able to still capture that, but can we quantize the model without actually having to go through that entire training process all over again? So we instead look at taking a teacher model that has gone through all this sophistication and to be able to be, let's say, chat enabled, as they would say. So the Llama 2 chat could be the teacher model, and that's in FP16. And then our student is the same model essentially, except that it's got Int4 weights instead of FP16 weights. And we can think about, from the knowledge distillation standpoint, there's this notion of having logits very closely aligned in terms of a loss, like KL divergence, but then also we can tie in with any data sets that we know were useful for pre-training the model or fine-tuning the model. And then we can inject that too and have some direct cross-entropy also as part of a loss to help guide the training process. Overall, this allows us to quantize the model and bring it to a very good gap from the teacher model. In terms of, if we look at perplexity, which is a common metric for how good a model is in terms of its next word completion or text generation, it's less than a 1 point in terms of the loss. And then if we look at accuracy of, let's say we take the model and we put it into a set of tests like common sense reasoning tests, and we look at the answers it produces relative to the teacher model, we're able to reduce this to less than 1% in some of those accuracy benchmarks. So this is a very promising technique that we can introduce if the task itself and the model itself is not necessarily amenable to simpler post-training quantization techniques. Now, this aspect of doing quantization helps us to reduce the target model, or the model that we're starting with, the teacher down to the student. There's things that we can do that are more dramatic in terms of getting the bandwidth reduction. And this is one technology is speculative decoding. Now, the idea of speculative decoding is that now instead of having one model that's really small, we have two models. One model that is the original one we wanted, at the bottom, this Llama 2. It may be quantized 2 with little to no loss. But then we introduce a very small model, which we call a draft. And the goal of the draft is to generate candidate tokens. And those candidate tokens would be used to send to the larger model, which would be just now in charge of verifying and correcting instead of generating the tokens from scratch. And interestingly enough, if we look at the compute and bandwidth requirements of verifying draft candidate tokens, it's much cheaper than generating tokens from scratch, because we can go and take, let's say, 4 tokens together and look at them in parallel through the model. And that allows us to have much less bandwidth movement, but be able to handle now 4 tokens instead of 1. And the nice thing about doing this also is that if the draft is reasonably accurate, like let's suppose it's getting 2 out of 4 tokens accepted, that's great, because that means that we've doubled the token rate, essentially, relative to not having a speculative decoding draft. So this is something that was also, say, demonstrated earlier a couple of weeks ago. I'll say actually more about that later. So what becomes a challenge here is orchestrating the system, of course, getting the target model at the bottom to be able to verify. But the draft plays an important role. And we have to make sure that we can have a good draft design. So, so we think about what are the challenges, what are the motivations. A draft model, we would like it to be much smaller because then the cost is incremental, minimal, almost negligible in some cases. We want it to be able to generate results fast, but we also, it helps us to generally reduce the memory requirements. So we can trade this off in many ways. Two obvious ones are we can generate more tokens for the bandwidth limit that we have, or we can meet the requirements of how fast we need to generate the tokens and then really reduce the amount of bandwidth and activity among the computations and chipsets to be able to meet that token rate. And now on the challenges side, we do very similar to the quantization. We do want to build a draft that really reflects the teacher as well as it can. It's going to be a much smaller size, of course, but we don't necessarily have the training pipeline that these LLMs have, these sophisticated training pipelines I talked about earlier. Interestingly, there are other things that we can do in draft, in this particular way of speculative decoding, where we can have one draft that it addresses multiple models of the same family. So sometimes models are released in essentially the same training goes through them and the same architecture is there, except that they're just different sizes. Like Llama has 7, 13, 33. OPT has an even finer granularity. And within that, if we train for one, we might actually be able to cover some of the other bigger models even beyond that. And so that's a nice single solution that can scale. And of course, the goal is that it gets enough tokens right in order to have a nice acceptance rate and from that acceptance rate, be able to speed up the token rate eventually at the target. So looking at this from our research standpoint, we were able to produce a good draft that's tuned to Llama 2 and have a good acceptance rate. And this is what we were able to show a few weeks ago when we had 20 token per second demonstrated on Snapdragon, the Gen 3 smartphones a couple weeks ago. So this one, we took the chat model at 7 billion, because that one is we know from a challenge standpoint that it has gone through a lot more sophisticated training. And then from a use case standpoint, that's actually the one that's nicer to interact when we want to tie it in with use cases that involve AI assistance on your applications. And then to give you a sense of when we demonstrated this, what exactly went into the demonstration, I have a diagram to give you that idea. So the LLM itself and the token generation is a part of the applications that we eventually want people to benefit from generative AI. The idea that it can sort through a lot of the capabilities of your device and help you manage it because of the complexity of all the things that are available are getting to be high, and it's nice to be able to sort through these and have some assistance sort through them. In the particular case, we also wanted it to be voice-based. So our AI assistant, which is chat-based, has multiple things happening on it. First thing is, if I look at this diagram, we have a voice activation happening. And this is both understanding when you're talking, having like a keyword like OK Assistant. And then also, once it's activated, we need to transcribe what you're saying with automatic speech recognition. So Whisper Small was a model that was used, and then we put that together. And generally, that becomes our interface so that you can interact with the device just by speaking to it. And then when it goes in, it's important to have some kind of orchestration here, because as an assistant, you would like it to be able to interact with software, not just necessarily produce tokens in response to what you're saying. And so orchestrator is important to know at what point are you speaking and would like a chat response? At what point are you speaking and what you're saying needs to be put into an API, like a form, so that it can be sent off to the software. And so this is a place where, putting these together, we have the orchestrator coming in and deciding how to route these to the actual chat model. And then the orchestrator also is deciding based on how that text has been classified. And a smaller LLM is there to help classify and understand what aspects should be processed for the prompt. And overall, this is where we were able to essentially demonstrate that we have an AI assistant that we shared at Snapdragon last year. I'm actually not leaving I'm leaving the sound out just to be easier for today's presentation, but you can see how just get a feel for what the interface is, how responsive it was, and generally how much we could interface with it. And could ask questions, we could go back and forth, revise itineraries, and then it would go and launch application to give us a set of itineraries from a particular website that had that. So, so as I mentioned a couple weeks ago then, this is where we had demonstrated the world's fastest in terms of the token rates, because we were getting Llama 2 running at 20 tokens per second back then at the summit. And these were two instances where we had just general chat. You could ask it about, at the time this event was in Maui, so they were asking it about various things related to Hawaii, or you could go into this orchestration with software, and as an example, we had a trip planner built in, and you could talk to it in multi-round dialogue to figure out your itinerary, all the details related to making requests, and then sending it off to the web. It's important to note that when we have a faster token rate, it's a lot of times there are applications on the right where we're doing planning, for instance, into the API, where tokens are not necessarily generated to be seen by the user. And so fast token rate's important there because we want to be able to do all that processing and not have too much delay from the user's perspective. Sometimes a token rate may be so high that it's generating words faster than a person can read, but that's just for chat. If we look at applications, it's important to also do that because we need to be generating more and more underlying decisions. So wrapping up this section now, we can look back and think about that full stack research design around making LLMs run more effectively, both in terms of efficiency, in terms of speed, and so forth. We started off thinking about where the bottlenecks are in running LLM on target. And then from a system optimization standpoint, there are things that we can do to quantize the model, things that we can do to introduce a draft for speculative decoding. And then there's the model efficiency aspect of getting those target models quantized and maintaining good accuracy. And then coming back to the AI stack and then the HTTP accelerator and then the NPU accelerator, that's where we can see again the realization of all of this technology end to end, and then realizing and then seeing it on your device in an application. Now, coming back, once we've started looking at GPT on the edge, Stable Diffusion on the edge, it's gives us also good hope to be complementary to where the cloud is, because these generative AI applications are many orders of magnitude larger than previous AI applications. And add on top of that, the adoption, the broad adoption that can have in various applications, web search, personal assistant, etc. Now that, and because they are of a more natural interface, like language and images or videos, they can nominally scale up to billions of users. So this is also the reason why we're very motivated to bring much of this to the edge, is because it helps us to really bring AI to everyone. The scaling that we need in the cloud could be prohibitive if we try to do everything just in the cloud. There's a lot of complementary aspects that we can do. And this is where we start to talk about hybrid AI. And as I said at the beginning, Qualcomm has always been focused on completely pushing the edge of wireless from a delay standpoint, from a power standpoint, from a latency, from a throughput standpoint, so that we can always bring that the latest cloud capabilities to the edge as much as we can. At the same time, we complement that by bringing the compute capabilities even further so that we can bring more and more of that technology from the cloud to the edge. And it's been this nice design evolution that has been going on. And now generative AI is the next inflection along this. And for reasons I've told before, having things on the edge also has its core benefits of cost and energy and privacy and so forth. So with this in mind, there are some interesting areas in generative AI where a hybrid AI design is unique. Let me start with what we would say is like a device-centric hybrid AI. This is like the most natural, intuitive way to think of things. If you have a smaller model at the edge, it can handle a lot more tasks that are simple. And it might turn out that a lot of the tasks through the course of the day are simple, so we don't necessarily have to send it to the cloud. And so it's natural to think of it. And either the local model itself can decide, or there can be some other rule-based arbitration of when we go to the cloud and when we stay local. Now, another important aspect for splitting processing is when we look at more rich interactions, like with the camera, with speech, with other modalities, it's nice to absorb as much as we can the delays and reduce the throughputs of sending raw information back and forth. And so this is where we have this notion of device-centric hybrid AI, where we might be sending instead just a reduction of the information that needs to go to the cloud, like text, or just getting text and text answers back, or a mix of text and some other embeddings. And then we might even further advance that by putting an orchestrator in the edge so that there's some improved prompts that can come from it. And that orchestrator itself might be a smaller LLM or smaller LVM. And so this is another natural way that we can look to enrich the experiences between the edge and the cloud. And then finally, there's a notion of, can we process things jointly between the cloud and the edge? And this is where, not too far off from the speculative decoding I had earlier, we can let whenever the smaller model cannot handle the tasks by itself, it can provide a draft response or other pre-processing to the large cloud model. And then it's just the job of the large cloud model to go and verify and correct. And from our standpoint, LLM limitations that we look at some of them are fundamental. Whether or not the edge or the cloud, it's going to have a bandwidth limitation. So it is beneficial even at the cloud side if we give it more tasks that are about verification and simple correction rather than pure token generation from scratch. And so when we look at this interplay between the cloud and the edge, we can start to think about benefiting by reducing some of the complexities in the bandwidth movement that's happening in the cloud itself, and then seeing if we can leverage that by being able to provide this connectivity and this orchestration across the edge in the cloud. So you can see now this is the last part of where generative AI is and can take us. And so in closing, we'll just reflect on the things that we talked about today. Thank you for sitting with us. And it's quite a lot we want to cover, but we have a lot that we're doing that we're really excited about. So I think trying to give you a more of a holistic picture was our goal, even though it is quite a lot that we're scanning through. But generally, coming back to the themes, we do have that on-device generative AI has a lot of benefits, even for enhancing what is offered in the cloud. And we wanted to get people a sense of that it's happening now, and we're bringing this to the edge, and there are more innovations coming that can help this become more and more effective. And generally, yeah, we hope to continue updating everyone on how research is progressing, and then affecting the ecosystem so that more of this can be seen. With that, I'll move to questions. Let me just mention that there are different ways that you can connect with us. We have, going to our webpage, of course, there's a lot on AI research that you can learn about, and videos across Qualcomm and AI research, mobile computing. Also, we have Twitter. And I, again, would like to thank everyone for tuning in today. I hope this was, I hope you found it exciting as we did, and look forward to your questions.
Thank you, Joseph, for the great presentation. As a reminder, if you have questions related to the material, please submit them using the Q&A feature of the interface. We already received a ton, so we'll get through as many as we can.
Sure.
First question, for fast stable diffusion, can you still go to lower steps?
We are, yeah, it's a great question. It was quite a feat to get sub 1 second, but believe it or not, that there are still multiple iterations sub 1 second, and the team is curious to see how much further we can go. So that is like an area of research, I should say, at this point. But I'm glad you asked. It's about as far as I can say right now. I'm looking forward to the future.
Great. You made a huge improvement in on-device stable diffusion in less than a year, going from sub 15 to sub 1 second. How do you see this trending in the future?
Yeah, thanks for the question. So in the future, I think the natural question that comes after you see things sub 1 second is, can we get them at like an FPS that's good for video? There's a lot of things that we do are actually grounded in video. So that's an area that's interesting. Within image, what's also emerging is a lot of the features that come from diffusion models are very powerful features. And so maybe from a perception standpoint, that may be something that gets exploited more too. And so it's not just about image generation anymore. It's actually could be more canonical in what we do. This is being acknowledged in a lot of research that's happening right now broadly in the research community. And this is something we kind of look forward to also.
Great, thanks, Joseph.
Question
about LLMs.
I forgot to mention also. Sorry. There are many other modalities related to vision too. So there's, as you can imagine, there's 3D is coming. We can always also look at audio and other waveforms too. So yeah, stay tuned for those.
Okay, another question, but this time about the LLMs. LLMs seem incredibly inefficient in terms of how tokens are generated. Do you think a future architecture may address this and make the models less bandwidth hungry?
Yeah, great question. Certainly, that is on the top of a lot of minds these days. The interesting trade-off to understand too is how well do the models train. So we do see that there are actually proposals for ways of generating tokens efficiently. Speculative decoding was one of them we talked about today. And we would, an important aspect is like how much can these get upstreamed into the pre-training of the model? Because kind of what we did in our example was model was already trained, and then we introduced a draft, and then we sped things up and made things much more efficient after the fact. There are actually other interesting ways that very, very early research that we're seeing that may be improving other aspects of handling models that can be done at the training side, like how to handle context length more efficiently. But we'll kind of have to see how that scales and how much that gets adopted.
So I'm trying to get through as many as we can, but
Sure.
we're not going to be able to. But for speculative decoding, how did you decide the model size for the draft model? How accurate does the draft model need to be to achieve these speedups?
Yeah. So the size itself, there was a bit of a, let's say, some some trade-off analysis you can do in optimizing the size, because there is some latency as size introduces, as it's generating draft tokens. Um, so that's one aspect. But once you get it below a certain size, it's sort of minimal impact to the overall processing timeline, you could say. Now, the accuracy itself, it's not going to be as accurate as the target model, of course, but it just has to have a very good acceptance rate. And even, let's say, like a 50% acceptance rate, if 2 out of 4 tokens are getting through, that means that we're actually getting, let's say, uh, doubling the token rate of the target model, and that can be a substantial gain. Intuitively, the draft is just trying to complete the next word. So as we go through languages and certain tasks, you can imagine it's easy to predict what the next word might be if you're given a hint from a correction from the teacher.
Great. We received a lot of questions about accuracy, so
Mhm.
maybe you can address it for
Sure.
both LLMs and LVMs, but there was some accuracy loss in your full stack AI optimizations, even if minimal. Do you
Hmm.
have a sense for what was lost and why?
Yeah. Yeah. Good question. In some of the, let me start with the LVM side. In some of the accuracy, let's say, those losses that we report are somewhat more about looking at these metrics that maybe are deeper in the features that are generated and how they relate between models. So whether or not perceptually they are different, it's a little harder to quantify. Meaning we can put it in a like a user preference score. We played around with a few of these. We could see, okay, sometimes the original model was chosen more often than the distilled model. Not to say that the distilled model had artifacts that were obvious. It may just be that um, people had a preference to the larger model. Now, there are some things where there could be artifacts more directly related, because in our particular case, we had a demo quality model, so we didn't train with as large a data set. Um, but I think that would be more about the data set than about the quantization and the distillation. Now, on the LLM side, we had on the target model, when we look at downstream scores and other metrics, yeah, we look and see of that 1% exactly what is not being solved or what is coming out wrong. And yeah, nominally, uh, like we in places where the target model might hallucinate, maybe it hallucinates a little bit more, and then it ends up with like a maybe gets a few of those questions wrong in the big set of questions. But overall, yeah, we're generally keeping in with a large body of what the common sense reasoning bench was. What that benchmark was consistent of, and make sure that we can address a large percentage of it. So in this case, was like greater than 99% of it. So.
Great, thanks, Joseph. A lot of questions about people wanting to do this themselves. So it's great
Sure.
to see Qualcomm doing things like knowledge distillation in so many places to solve challenges for quantizing and training. Um, what level of knowledge does a developer or ISV need, or an OEM, to do this on their own? And do you have any tips and tricks?
Sure. Yeah, that's a good question. So one thing important that is on our mind is there is a large infrastructure nominally needed to train some of these models from scratch, and we don't expect everyone to be able to have that. But we do feel that maybe a broader capability is, can people run the model in reasonable, like FP16 and at a reasonable scale for inference, so that as they're developing and testing application, and then can they fine tune the model? And they may also want to do a fine tuning for their own applications anyway. So given that the developer or researcher may have that capability, then they can start thinking about some levels of distillation, some levels of some of the quantization tools that we're introducing, and then from there they can reproduce some of the things that we're doing. Not everything on the vision side necessarily can be done with reduced compute, but on the LVM side, but we are like some of them can, and we are very. It is an important aspect for us in our research to understand at what level and what tooling do people need to reproduce this.
Great, thanks, Joseph. We're at time, so I wanted to finish with a futuristic question here. Okay. What's next after LLMs and LVMs?
Oh, all right. So some of the obvious ones that are next, and I think they're next in the sense of they're happening already, and we're just maybe bring it to the edge. But multimodal is like a next big thing, I would say. It is natural to think about the prompt having video in it, or prompt having image in it when you're having assistant interact, answer your questions. And another important one is, as we go to multimodal, we also have an opportunity. Actually, our multimodal already started in terms of having voice. When I say multimodal, I actually mean more about image and video. But even a few weeks ago, we had voice with LLM. And the next step is, now that you can speak to it, it can be more predictive. So right now, it was just detecting whether or not you're speaking, and then it kind of addresses a prompt that you give it by speaking. But then it can be more predictive in understanding, maybe it should talk to you instead of wait for you to talk to the AI system. And we can extend that to multimodal. Like if the camera is watching you, it can decide when it should interact, who it should interact, what's the context of how it should interact. And then it's not just about the camera anymore too. If there's an assistant on your phone, there are a lot of things happening on the phone, like the applications that are in the foreground or in the background. Depending on how we enable it, it can be predictive about when to bring things to your attention and how to interact with you, which should speak with you, should it prompt you, and so forth. So being predictive is another exciting place that we feel is ahead for AI assistance. And the modalities is another exciting place between LVM and LLM that we're looking to get.
Great, thanks, Joseph. That's an exciting future, and I think that's a great place to end. So on behalf of Qualcomm and on behalf of Joseph, our presenter, thank you for joining us today. The webinar will be available on demand, and have a great rest of your day. Bye.
Thank you, everyone.